Everyone, Ms. Kilroy here. Today we're going to be talking about states of matter. So take out your notebook and turn to the next blank page. We saved this in our notebook, right? States of matter, full size, taking up the whole space. This is our new unit. We're not going to be talking about California, Oregon, Washington, not those states, but states of matter. Remember, if I'm ever going too fast, you can pause the video and write down what you need to do. So states of matter, the plain old definition is the physical forms in which a substance can exist. It's determined by how fast the particles are moving within the material. So we're going to be talking about 4 states of matter: solid, liquid, gas, and plasma. So we're starting as solids. As we add energy, they change state. So then it changes to a liquid, add more energy, turns to a gas, add more, turns to a plasma. But my question is, how do we add energy? So think about that for a moment. If we have a pot of water, we add energy and it changes to a gas. How do we add energy? And if you thought about heat or temperature, you're correct. So by heating up these states of matter, they can change states. So a solid has definite shape and volume. And the word definite means for sure. So I'm definitely going to the basketball game after school. So solids have a for sure shape. They have their own shape and their for sure volume, a definite volume. You can measure it if it's a perfect box. Length times width times height. In solids, the particles within have little energy movement. They can wiggle in place, vibrate, but they can't move past each other. And there are 2 types of solids. We have crystalline and amorphous solids. Crystalline is an orderly, 3-dimensional arrangement of atoms or molecules, and amorphous is where the atoms or molecules are in no particular order. So crystalline, think crystal, diamonds. So that is an example of a crystalline solid, salt and ice. Amorphous solids are bendable, so like rubber, wax, glass. So if you look at their structure, crystallines are nice and orderly, amorphous have no order. So on the left-hand side, please draw everything here. So we've got my 2 types of solids, crystalline and amorphous, and they have a definite shape and definite volume. Okay, go ahead and write that down. These little squiggly lines show that they are wiggling in place, shows the energy. So examples of solids, I'm sure you guys can name a lot more than these pictured, just to give you an idea. All right, moving on to liquids. Liquids have no definite shape. They just take the shape of their container. They don't have their own shape. But liquids do have a definite volume. You can measure the volume of a liquid in gallons, quarts. In our class, we use liters and milliliters. Liquids have some energy. They have more than solids, but they're still bound to each other, but they can slide past one another. And then characteristics of liquids, they've got surface tension and viscosity. Surface tension is the force attracting the particles at the surface of the liquid. So if you've ever been to Rocky Creek Park or any creek, there might be these little bugs that float on top of the water, and they're able to walk across the water. They're called water striders. And they're able to do that because of water's surface tension. It kind of makes a little layer where the top is very tight, and they're able to walk and not break that surface tension. Viscosity is a liquid's resistance to flow. A high viscosity liquid are things that move slowly, like honey, motor oil, syrup. A low viscosity liquid is fast-moving liquid, like water or rubbing alcohol. Examples of liquids. Again, I'm sure you guys can name a whole bunch. On the left-hand side, please draw the atom arrangement for liquids. So we've got our atoms, and these little arrows represent energy. So in liquids, they're just sliding past one another. So they have more energy than solids. And they have no definite shape, but they do have definite volume. Gases have no definite shape and no definite volume. So gases just take the shape of of its container. So if you're making an animal balloon, you can take that same amount of gas and make a sword or make a princess hat. You can change the shape of it. And particles have more energy than solids and liquids. They're not bonded to each other, and they move about freely, colliding with each other often. So pressure is the amount of force exerted in a given area. So the number of collisions of gas molecules on the inside of the container. So for example, go ahead and draw this on the left-hand side. So this is our molecular arrangement of a gas. So notice how the arrows are longer than liquids. And notice how the gas takes up the whole space of this container. So if we were to draw a smaller container, but still have the same number of atoms in there, there would be more collisions. So the more collisions means more pressure, so the higher the pressure is. So gases have a non-definite shape and a non-definite volume. So we can also change the volume of the gas just by, if we had a lid on this and we pushed the lid down, and then all of these molecules were down here, we would still have the same amount because they would just take the space of the container, but the pressure would be higher. All right, let's make sure you have all of this down. And then some examples of gases: helium. Anytime you see, smoke or steam. Inside Coca-Cola, they have bubbles. So bubbles is a gas. Carbon dioxide. All right, in our last state of matter, we have plasma. So plasma, just like gas, it doesn't have a definite shape or definite volume. Particles have a lot of energy. So plasma has the most amount of energy. Electrons are stripped free from gas, and they're also called ionized gases. Atoms or molecules are surrounded by escaped electrons. And plasmas can conduct electric current. They can be contained by magnetic fields. So for example, lightning is an example of plasma. Fluorescent light bulbs, like the ones in class, they have plasma running through the light. And then the aurora borealis, which is my favorite, also called the northern lights. You might have seen this in the Polar Express or Brother Bear, or maybe you've been lucky enough to actually see them in real life up in Alaska. So they just look beautiful and a pretty example of plasma. And on the left-hand side, go ahead and draw the molecular arrangement of plasma. Notice how these arrows, or this energy, is the greatest. So draw the arrows the longest out of all 4 states of matter. And plasma, again, has non-definite shape, non-definite volume. Okay, I want to show you guys a little video here.
What is a candle flame really made of? I'm at the Palace of Discovery in Paris to do an experiment that beautifully demonstrates the answer.
Ce conducteur-là sera chargé négativement, d'accord? Par ce phénomène qu'on appelle l'influence électrique, celui-ci sera chargé plus.
Okay, so we're turning on an electric field here. You can see that the flame is spreading out. Quel est le voltage ici?
Il doit être à peu près 20 000.
20 000.
On voit bien quel papillon ou non? Oui.
Papillon?
Papillon, ça fait comme ça.
Oui, oui, oui.
Comme un papillon.
Oui. That's very cute. It's like a butterfly.
Alors la flamme, c'est un plasma. C'est un milieu totalement ionisé.
And you can see that the flame has 2 separate pieces to it now. One is going towards the negative plate, and those would be the positive ions, and the negative ions would be going towards a positively charged plate. So we see the flame kind of flattening out. But if that didn't convince you that a flame contains ions, then check out part 2 of our experiment, where we compare the conductivity of a flame to the conductivity of air, which is normally a pretty good insulator. It requires about 10,000 volts to break down a centimeter of air. So right now, this plate is at about 10,000 volts. You see that the spark is only a little. But if I put it around the flame, let's see if we can get a bigger spark to happen. Look at that. Yeah. Because the flame has those ions in it, it means that we can break down a greater distance of air. There's greater conductivity. Yeah. That's awesome. You love doing this, right?
A strong enough electric field can actually extinguish the flame. But watch carefully what happens when the flame goes out.
Regarde,
Wait.
on voit très bien.
Il y a des ions dans la fume.
Oui, tout à fait.
Just like in the flame, the opposite charges in the smoke are pulled in opposite directions. Now, while some may argue that a flame is not truly a plasma because it's not hot enough and it doesn't have a high enough density of ions, one thing is for sure, it does contain ions which have important electrical properties which can be demonstrated if you have a strong enough electric field.
Regarde. Ah.
All right, I hope you enjoyed these notes.